Welcome to my maths presentation of Sumerian matrix factorization. My name is B. Vidaraguram from section CSC AML C, BTech first year. Introduction. We developed a generic framework for unsupervised discovery of regularities or patterns in rank data. In this type of data, each row is complete or partial ranking of available column. Rank data naturally occurs in many situations of interest. Consider, for instance, cycling competitions where the items are the cyclists and each transaction corresponds to a race, or a business context where the items are companies and the transaction specifies the rank of their quotation for a particular service. In social sciences, rank data has been used to represent users' preference over their favorite countries, residency candidates, or products. In biology, rank data has been used to represent the level of gene expression. In sport analytics, rank data has been used to rank sports teams. In general, ranking forms a natural abstraction from purely numeric data, which often arises in practice and may be noisy or imprecise, especially when the rows are incomparable, i.e., when they contain measures on different scales. Transforming the data to ranking may result in more informative representation. While rank data is ubiquitous, only few data mining methods have been developed for rank data analysis. We also contribute a rank matrix tiling method to discover rank tiles, which are data rectangles having high ranks. Each of these works aimed at a single type of rank pattern, and they did not aim at general framework for different types of rank pattern set mining. That is, a small, non-redundant set of pattern globally describing the structure of data. Matrix factorization has been used in many fields such as data mining, recommended systems, and bioinformatics. Depending on the constraints on the data for pattern users are interested in, one applies different forms of matrix factorization. For example, if the given data has non-negative value constraints, non-negative matrix factorization can be employed. Although matrix factorization has been extensively studied, it cannot be applied directly to rank data due to the fact that the linear algebra used in traditional matrix factorization method does not provide a way to aggregate or sum rankings over items. So heading towards our main topic, in this section, we first illustrate the rank pattern set mining problem. Next, we explain the different reasons why traditional matrix factorization approach based on linear algebra cannot be directly used for mining rank data. Then we introduce the Sumerian rank matrix factorization framework. Definition 1. Rank matrix. An M of n matrix M is an rank matrix M if and only if M in M, R, C belongs to, for all, 1 is less than or equal to R less than or equal to M, and 1 is less than or equal to C, and C is less than or equal to N, where sigma is equals to 1, 2, till N, union of 0. In our setting, column or items or products that need to be ranked. Rows are ranking of item matrix entry M. R, C indicates that column C is ranked M R, C through for R. The rank value 0 has a special meaning. It denotes unknown ranking. For example, in rating dataset, some items are not rated. Such item will have rank value of 0. Many different types of pattern can exist in rank matrices. We will first discuss the intuition behind the two such patterns. Example, consider the following rank matrix M. In red and blue, we indicate parts of matrix in which the rank is consistent for a subset of row and column of matrix. For instance, in the first two rows, the rank of items are identical. Red and blue here highlight pattern in matrix. Definition 2. Rank matrix factorization. Given a rank matrix M belongs to sigma M of n and an integer k, find a matrix C into C that belongs in the 0, 1. M of k and matrix F belongs to sigma k of n. P such that C, F is equals to argmax C, F f of m, Cf, where f is an where f is scoring function that measures the similarities between matrices, is an operator that creates a data matrix based on two-factor matrices. Intuitively, in matrix F, the row Fi indicates partial ranking. Column Ci of matrix C indicates in which rows the corresponding partial ranking appears. The following example illustrates this initiation of example. Sparse MRMF. In this section, we study the first problem instance of SRMF called sparse max product smearing rank matrix factorization, or sparse MRMF, which aims to find pattern of consistent rank such as illustrated in the example. This problem was first introduced in previous works and named sparse RMF there. Another example of sparse MRMF is provided below. This example shows a rank matrix approximated by the product of two smaller matrices. Rank matrix M consists of 5 rows and 6 columns. Assuming no ties and complete ranking, each row contains each of number 1 to 6 exactly once. Sparse MRMF factorizes matrix M into product of a binary 5 to 3 matrix named C and a 3 to 6 matrix named F. Each row of matrix F is sparse vector with many zeros and can be interpreted as a local pattern. Let R be the reconstructed matrix at factorization, that is, R is equal to C into F. We can say an entry R C, C is covered if R C, C is less than or greater to 0. We define coverage of factorization as follows. Max product, smearing, rank, max tiling. We study the second instance of SRMF called max product smearing rank matrix tiling, or MRMT. This problem was first introduced in our previous works and named rank tiling there. It aims to identify subsets of data with high ranks as illustrated in example. Another example of MRMT is provided below. This example shows a rank matrix in which regions with higher rank than 3 are indicated by means of two Boolean matrices. The matrix C identifies the row including in tiles. The matrix F indicates the columns. Real world case studies. European Song Festival data. The Eurovision Song Contest, or ESC, has been held annually since 1956. Each participating country gives voting scores, which are a combination of televoting and jury voting. Two competing countries' scores are in range of 1 to 8, 10, and 12. Each country awards 12 points to its most favorite country, 10 points to its second favorite, and 18 to 1 to third to 10 favorites respectively. The data can be represented by a matrix in which row corresponds to voting countries, columns corresponds to voting competing countries, and entry values to scores. The ESC dataset collected and processed The ESC dataset collected and processed by Levan et al. Consists of 44 rows and 37 columns corresponding to 44 voting countries and 37 competing countries. For final rounds of period of 2010-2013 running experiments, we ran sparse MRMF with various values for the threshold. For the threshold, that is, A belongs to 5%, 10% to 30%, for each of which we factorize the rank matrix with different k values, that is, k belongs to 5 to 12. The figure shows the average coverage and error scores for different values. It can be seen that for A equals to 5%, sparse MRMF made almost no mistake error, or error is equals to 0.04, but coverage is low, only 19%. When A is equals to 30%, on the other hand, sparse MRMF covers almost the entire matrix, 90%, while having an average entry-based error of only 5%. Voting patterns. The heat maps of the reconstructed matrix obtained by sparse MRMF and the covered matrix by MRMT are shown in are respectively. Compared to the original rank matrix, the two heat maps show that the two methods strongly sparsified the original rank matrix. The figures also show that the rank profiles produced by sparse MRMF contain both high and low rank, while the one produced by MRMT only indicates the place where high rank appears, as expected. Thank you for hearing out my presentation and hope you have a basic idea about my topic now.